Coming to the outcome of today's session, today we will observe the construction of BCD adder. Now during the previous session when we learnt about BCD or 8.4.2.1, this is the chart that we acquired, didn't we? If you remember, in case of BCD, we actually call it 8.4.2.1 because of the place values. And with these place values, we represent all the decimal symbols 0 to 9. Now to be really honest, with 4-bit places, we actually can create 16 different patterns, can't we? Basically, all the decimal numbers starting from 0 till 15. Now in case of BCD, these patterns 10 to 15 are invalid. So basically what happens when we add one BCD number with another BCD value, say the outcome that we got is 1010, that is this pattern. Now clearly from the chart we can say this is invalid. Basically for all 4-bit values, anything greater than 9, that is 1001, is supposed to be invalid. So how do we correct this? In order to convert one invalid BCD number to a valid one, we have to add the pattern 6 to it, right? So 0 plus 0 will give us 0. Now 1 plus 1 is 10, so we will have sum as 0 and the carry 1 will be added with this 0, resulting in 1. Now 1 plus 1 will again give us 10, so 0 will be sum and that carry will go ahead and will be added with this 1. So 1 plus 1 will again give us 10. Now 10 plus 0 will eventually give us 10. Now if we append 3 more zeros as the prefix, observe, this is now 0 in terms of BCD and this one is actually 1. So this is how we perform the correction. Let's now try to construct the BCD adder. Say we have a binary adder and we are feeding the numbers BCD1 and BCD2 as two different inputs. Now since it's a binary adder, we are assuming that the carry input is ground. However, we will also have the final carry output, that is C3, and the sum will be produced as S3, S2, S1, S0. Now this much is fine as long as these sum represent all the values starting from 0 to 9 only. Anything greater than 9, that is any pattern from this, if it is produced as sum, then that's the problem. So let's try to find the solution now. Now we will try to define a function f for all the invalid patterns. So what we will do, for all these invalid patterns, we will force the function f to generate ones. This will eventually help us in the generation of the correction, that is the pattern 6. Basically, from all the different patterns which can be generated from these, only these 6 will generate ones. So let's try to minimize this with the help of the K-map. Now if you observe our K-map carefully, notice here the higher order bits are specifying the rows and the lower order bits are going to specify the columns. Now K-map are actually formed using gray codes. And that's the reason why both the rows and columns are like this. 0, 0, 0, 1, 1, 1 and 1, 0. And the rows are also identical as the columns. Now following these organizations, the cell numbers will be placed like this. Now observe the first pattern, it is 1, 0, 1, 0, correct? Basically S3 and S2 are 1 zeros, so we will go to this particular row. And S1 and S0 is also 1, 0. So in this particular row, we will head in this particular column. Observe 1, 0, 1, 0. So basically we are referring to this particular cell having the value 10. And the function for that particular cell is specifying 1. So we will place 1 in here. Now to be really honest, these are the patterns of 10, 11, 12, 13, 14 and 15. Since we have all the cells numbered, using the cell numbers we can also fill them up. So we will place 1 in the cell number 11, then in the cell number 12, in 13, in 14 and finally in 15. Now observe, this is the first quad that we are getting. Now this particular quad will cancel out all the columns, so we will be left with this row value, which is S3 and S2 in uncomplemented form. So our function will have S3 and S2. Now proceeding forward, we can observe this is the next quad that we are getting. Now for this particular quad, if you observe the rows, in these two rows, S2 is alternating the value. So that will cancel S2 out. And since S3 is same, so S3 will be retained. Now this particular quad also involves these two columns. Now if you observe, here S0 is alternating the value, so that will be cancelled out. Since S1 is retaining the same value, so in our function we will have another min term, that is S3S1. Now with the help of this expression, let's try to find our solution. So we will have another binary adder where in one line of inputs we will send all the sum. Now we also need to figure out this particular expression. So first let's construct S3 and S2. So if we feed these two lines in this particular AND gate, this will eventually result in S3 and S2. Let's now construct S3 and S1. So this particular AND gate in here, since it is getting the input from S3 and S1, it will eventually produce S3 and S1. Now we need to take care of this OR. So these two will finally be fed into this OR gate. Now in this particular binary adder, in one of the inputs we are feeding the sum. Now say the second input is n, that is n3, n2, n1 and n0. This will help us with the correction. Now if you remember, the correction pattern was 0, 1, 1, 0 or the pattern of 6, right? Keeping that in mind, we are feeding n3 with 0 and also n0 with 0. Now we have configured our function in such a way that in any particular instance, if these sum generate any of the invalid values, this particular circuit is going to produce 1, right? So that one we will feed in n2 and n1. Now try to understand this logic. At any given point of time, if the sum produces any of the invalid patterns, then only we are going to use the correction, right? And the correction is pattern 6, which will be generated by this. However, if the obtained result is valid, then through n2 and n1 we will get only zeros, right? So basically the valid BCD will be added with 0 only. Now if you remember, in the previous session we observed that not only for the invalid patterns we are going to use the correction, we also will have to use the correction if the carry is generated, right? So we need to modify our function like this. Say our final function will be f1. Now in f1 we will definitely have f, and along with that we will also have c3, that is this carry. So let's construct this. All we have to do is feed this carry into this OR gate. Now this circuit is complete. So now this binary adder will produce the result as R3, R2, R1 and R0, which is going to be a valid one. Now alongside this, we can also expect a carry. Now this particular carry will be stored in a register's least significant place where all the most significant bits will be cleared with zeros. So this is the finalized BCD adder which we constructed with the help of this logic. Let's now observe the invalid number of inputs for this particular BCD adder. Now we actually have two different BCD numbers, right? And these are of 4 bits, aren't they? Now with 4 bits, in both the cases we can have 16 different patterns, basically 0 to 15. Now in terms of BCD, we will have only 10 valid patterns, that is 0 to 9. So the total number of input combinations which is possible is 16 into 16. However, total number of valid input combinations will be 10 into 10. Now 16 square is 256, and this is the total number of input combinations possible. Now from this, if we subtract 100, that is 10 squared, we are actually subtracting the number of valid input combinations from total number of combinations, which will eventually give us 156, that is the invalid number of inputs. So for 4-bit BCD adder, we actually need to be concerned about these 156 invalid number of inputs. So in this session, we observed the construction of BCD adder.